question 3 is to do with electrochemistry. So what are we doing? We are trying to measure electropotential of iron 3 plus and iron 2 plus. So this is what I call metal ion and metal ion. When you want to measure electropotential of metal ion and metal ion, this is the third case study, of which the first two involve metal ion and the metal. Okay, then you use the metal as the electrode. Non-metal ion and non-metal, then you use a platinum hydrogen electrode, okay, such as this, right? And here, this must be the standard hydrogen electrode because we are trying to measure standard electropotential. So this is the standard hydrogen electrode, meaning C must be the 1.00 mole per dm cube acid, so you can use HCl aqueous, but not H2SO4 because you want it to be monoprotic acid, or sometimes they call it monobasic acid. So 1 mole of it only give you 1 H plus. All right. B is the platinum electrode because it's part of the conducting electrode for the standard hydrogen electrode. Okay. A is your hydrogen gas. So I'll just write down hydrogen gas. If you want, you can write down H2 gas. I think you should be alright if you write down platinum solid, but it doesn't hurt to write down platinum like that, I guess. They ask you to D as well. D is the salt bridge. Typically for our salt bridge, we use something which is soluble, like KNO3. All nitrates are soluble, obviously. Okay. Well, aqueous, so dissolve in water. This is your other system, so this must be your Fe3 plus, Fe2 plus. I say system because E cannot be Fe3 plus or Fe2 plus, because for investigating or for getting the electropotential of this, you need it to be a inert electrode. So you also need it to be platinum electrode as well, simply because it is not a metal and metal ion, it's a metal ion and metal ion. The third case study as stated in your syllabus, which you will have learned from your classroom lesson, which you listen in class, which you make your own notes, and which you revise, which you will know. Okay, so the solution is equimolar. So what we will have is we will have both iron 2 plus as well as iron 3 plus. So this iron 2 plus aqueous, and okay, so it's equal amount of standard concentration of iron 2 plus and also iron 3 plus aqueous, and that's very important there. Okay, and I forgot about this. This is supposed to be a high resistance voltmeter. So the whole idea of using a high resistance is to have the maximum potential difference that will be indicated by this high resistance. It will allow maximum potential difference between the two systems to be recorded on this voltmeter. Label the diagram to show which one is the positive electrode and the direction of electron flow. Okay, electron flow towards positive terminal. Positive terminal would be the plus. Plus will attract the negatively charged electrons. Let me think. We are thinking about where the electron is flowing, right? So use the data booklet to help you. Well, we have the E naught of H plus H2, which is 0.00 volt. And then you look for the one which is iron 3 plus, iron 2 plus. Make sure you read the correct one from the data booklet. Just opening my data booklet right now. So the electropotentials are arranged in alphabetical order. So the first one you see involving Fe is the wrong one because there's iron 2 plus and iron, there's minus 0.44. The second one is iron 3 and iron, there's minus 0.04. You're looking for iron 3 reduced to iron 2, so there is plus 0.77 volt. And because this is more positive, so this is the E red. E red means reduction takes place there, so reduction takes place here. So reduction is here. Okay, and reduction involve electrons being gained. Reduction is gain of electron, OL-RIC. Those are your mnemonic from O level or IGCSE oxidation and reduction, which you cover again in your AS level, electrochemistry under redox. So you gain electron here because you gain electron here, the electron must be flowing here. Okay, because this is the more positive E naught. If it is the more positive E naught, it's the E red. E red is where reduction happens. Because reduction happens here, electron is being gained here. And if electron is being gained here, the electron is flowing that way. And if the electron is flowing this way, electrons are negatively charged. The negatively charged electrons will be attracted to the positive electrode. So this E must be the positive electrode. So which one is the positive electrode? E is the positive electrode. So this is the positive, hang on. E is the positive electrode. Okay, so I should probably rub that out. Positive electrode. So that was part 2. Okay, so and then part 2 is also to do with the electron flow. So electron flow towards the positive electrode. It will flow towards the more positive E naught value. So electrons flow here, okay, because reduction happens here because it is the E red. So I hope that makes sense. Not too bad for 1 mark. So it's a definition. So these are straight from the syllabus. Standard cell potential. That theta there refer to standard conditions. So standard conditions of 298 Kelvin, 1 atmospheric pressure, and because we're dealing with concentration of aqueous solution, we're talking about 1.00 mole per dm cube. And this is a cell potential. They could also ask you standard reduction potential, or actually standard reduction potential. Together, standard reduction potentials that make up the redox reaction is used to calculate the cell potential, right? And there's also the standard hydrogen electrode as well. Pretty stingy for that 1 mark, but anyway. So E standard cell or standard cell potential is a measure of the tendency. So somewhere along this line, I guess you don't really need to, have the exact same definition, but it's to do with a value that you have in volt, right? That's the unit of the quantity that you're measuring with a high resistance voltmeter. In fact, I need to just draw in the high resistance voltmeter just like that. Okay, so that is your high resistance voltmeter in order to measure the cell potential, the tendency for the electrons to flow through the circuit, or in this case the external circuit as defined by the syllabus, under standard conditions. I guess the standard conditions are the really important thing, but just by mentioning the standard condition, I don't think you will get the marks because it's not a standard condition. This is a standard condition, but what does the value actually tell you? Okay, so again, very stingy for that 1 mark alone. Doesn't matter, there might be some easier bit to score here and there, so don't lose your marks on definition like this. Always try your best to go in being prepared. If you fail to prepare, you gotta prepare to fail, right? Okay, so it's not a difficult paper so far, and don't forget labeling the components you add. This is not a complete circuit because, well, it's not a complete circuit. I need to add something called a salt bridge. So that is the component I added, but there are already some component in here. You want to measure the cell potential consists of iron 3 plus, iron 2 plus, and then the Ag plus and the Ag. Okay, so for the Ag plus and Ag, this is one of the 3 case studies stated in the syllabus under A2 Electrochemistry. This is metal. This is metal ion. So in the syllabus, it says to measure electrode potential of metal and metal ion. So you will need metal as the electron. The next one is to do with iron 3 plus, iron 2 plus. So both of these are metal ions. So when you have metal ion and metal ion, you need an inert electrode, which you can use platinum electrode. Okay, so completing the diagram, don't have much choice now, do I? because we don't really know left or right, so it doesn't really matter here, because there's no labeling of cathode or anode yet, and we'll decide which direction does the electron flow depending on where we put the electrodes, and there will be one direction from one place to another that it will flow based on the electrode potential in the data booklet. Okay, so if I put this left hand side as this thing here, for no special reason, so A will be the electrode, so it's the silver electrode, so it's the metal itself, so you can use silver electrode, and then for the solution therefore will be Ag plus, so don't forget is standard condition, so 1.00 mole per dm cube. Ag plus aqueous, which you could use a soluble silver salt, which silver nitrate is a very common one, because all nitrates are soluble in water, which means this other half cell would be for the iron 3 and iron 2. I would need a platinum electrode in inner electrodes, and I will have equimolar. So in the same volume, I have 1 mole per dm cube iron 2 plus aqueous, and it has got to be both of them, 1 mole per dm cube equimolar. Okay. Now use the E0 values to write an equation for the cell reaction that take place if the two electrodes are connected and when the circuit is like that. So if I copy this down from the the data booklet, these are how we always write it, as the reduction potential as you see it from your data booklet, not periodic table. I don't know why I keep on saying data booklet. I keep on saying periodic table when I want to say data booklet, and I keep on saying data booklet when I want to say periodic table. Very annoying. Anyway, so iron 3 plus iron 2 plus you show as reduction. You have to choose the right one, because this is metal ion and metal ion case study, metal ion and metal ion, so you got to choose the right one from your data booklet. Okay, I got it right this time. Oops, I got it the other way around. So the silver plus and silver is plus 0.80 volt, this one is plus 77 volt. As you could see, this one is more positive, and if this one is more positive, it prefer to be reduced. Okay, therefore it's the E red. So the cell reaction that will happen is where your E cell is greater than 0, then your delta G is lesser than 0, then the reaction is spontaneous. But we want to use E0 values to write an equation, for the cell reaction that will happen. So we're saying that the more positive one will be E red, so the more positive one will be the reduction, so the silver go to silver like that, and then that will react with something which is E-ox, so we are saying this will be the E-ox, which means it go from iron 2 plus to iron 3 plus, so I have plus iron 2 plus going to iron 3 plus, 1 silver, 1 iron and 1 iron, plus 1 plus 2 is plus 3, 0 plus 3 is plus 3. So there's your equation for this reaction that will take place, because if you calculate the E cell, it's going to be plus 0.80 E red minus E ox, which I don't need a calculator to tell me. Your calculator will show you 0.03, but sign, value and unit are very, very important in physical chemistry. In the previous question we had chemical energetics, enthalpy, entropy and Gibbs. Here we have electrochemistry, same thing, sign, value, units. Okay. So now they're trying to relate that to standard electrode potential. I bet there's some electrochemistry that I'll ask you in a little bit. There's 2 mark here, because there's 1 mark for the standard conditions, 298 Kelvin, 1 atmospheric pressure. We are talking about electrochemistry, so we are talking a lot of solution, so 1.00 mole per dm cube. Remember that electrode potential is to do with potential difference, so it is the potential difference, and they are all measured relative to a standard hydrogen electrons. I was going to write potential electron. It is the potential difference between a standard hydrogen electrode So you know the hydrogen gas with a platinum electrode and a 1.00 molar H plus, which come from HCl or HNO3. And you have a metal, which is the electrode. A lot of the definitions they use a metal, but of course it could also be a non-metal, which then you need a platinum electrode. But the idea is that you must have an electrode immersed in a solution of 1.00 mole per dm cube. So this is the other side where you must have a solution of 1.00 mole per dm cube under standard conditions. And of course, I guess you get 1 mark for getting all the standard conditions correct. 298 Kelvin or 25 degrees Celsius, 1 atmospheric pressure, 1 atm pressure, and I'm just rewriting this just in case, 1.00 mole per dm cube concentration. See, they actually include a bit of electrochemistry here. So we have a cell to measure the standard electrode potential of a cell. So you have a metal and a metal ion. So this is a metal and metal ion case study. The other one here is a metal ion and metal ion. If we look in the syllabus under electrochemistry, there are 3 different systems that you need to know: metal and metal ion, non-metal and non-metal ion, and then you have metal ion and metal ion. For the metal and metal ion, your electrode is going to be the metal itself. For metal ion and metal ion, your electrode is going to be an inert electrode. We use platinum. For non-metal and non-metal ion, you'd also use a platinum electrode. Okay, write an equation for the overall cell reaction. So if you look at the thing here, this is going to be cobalt 2 plus 2 electrons giving you cobalt, and then this is iron 3 plus electrons giving you Fe2 plus. These are straight from the data booklet, but of course any competent chemist at A level, you should be able to write this very easily. +2 -2 no charge, +3 -1 +2. Okay, so write the equation for the overall cell reaction. So what are we doing here? What is reacting with what? I think you really need to look at the data booklet for some values. So if we go straight to the data booklet, you can see where am I? Hang on, let me open up my data booklet. So make sure you read the correct one. So they are in alphabetical order. So cobalt 2 plus going to cobalt is minus, the E naught is minus 0.28 volt, and the iron 3 plus going to iron 2 plus. Iron 3 plus can go to iron, that is minus 0.04. We are looking for iron 3 plus going to iron 2 plus, which is plus 0.77. Since between these two values, this is the more positive one. If this is the more positive one, this undergoes reduction, because the more positive you are, the more you favor the reduction process, favoring the right hand side. If that is the reduction, then we are looking at Fe3 plus reacting with cobalt, because this is oxidation, whereas we have shown reduction here because this is how the data booklet will have shown us as a standard reduction potential. So to show oxidation is loss of electrons, then I could show cobalt going to cobalt 2 plus 2 electrons, and then the iron 3 plus electrons going to iron 2 plus. Of course, this is 2 electrons being lost, this is 1 electron being gained, so you need 2 of it in order to cancel out the 2 electrons and 2 electrons, such that my equation would involve 2 iron 3 plus 1 cobalt, giving you cobalt 2 plus 2 iron 2 plus. Alright, so I'm just going to rub that out because that looks a bit messy. But how we can see that as a result of these ERAD and EOX values, it has to be this plus this rather than this plus this on the left hand side, because the next part really they ask you to calculate the E cell. So the E cell is going to be the more positive ERAD minus the EOX, and the ERAD is the plus 0.77, we don't multiply by anything at all. Oops, I just said we don't multiply by anything and I went to do that. Use bracket. We don't change the sign of anything at all because these are standard reduction potential value as given in the data booklet, and it's already taken into account by the negative there, so we do not change the sign or anything, just put it in. We use bracket, and with the use of bracket, how you can see that on your calculator, they will eventually add up because of the minus. So be very careful on your calculator. This is what your calculator shows you is actually wrong. Anything to do with physical chemistry is essentially physics. We are talking about sign, value, and also unit. So plus 1.05 volt. When you have E cell bigger than 0, you have a feasible and a spontaneous reaction, because when E cell is greater than 0, your delta G, which is your Gibbs free energy, is lesser than 0.